Namaskaram. In this session, we will discuss about coordinate of a vector in a vector space. The main advantage of coordinate is we can convert everything in terms of numbers in a vector space using the concept of coordinate. In last class, we have seen that basis and dimension of a vector space. And this is your question, the dimension of Pn. Yes, what is the dimension? Yes, n plus 1. Why? You can construct a basis, at least one basis, that is like this 1, t, etc., t raised to n. It is clear that this is linearly independent and you can easily show that this set spans Pn. So this B is a basis. This is a basis. Every vector space has several bases. Anyway, this is a basis. So it contains n plus 1 elements. So dimension of Pn is n plus 1. Okay. Consider this problem. We have to check whether this set is a basis for R square. So let it be V1 and V2. So we have to check whether this set is a basis. That means we have to check two conditions: linearly independency and span. Right. So first we have to check this set is linearly independent or not. And also this set contains only two elements, right? Only two elements. So we know that for a two element set, linearly dependent if and only if one of them is a scalar multiple of other, right? It's a result in previous session. So you simply check whether one of them is a multiple of other, is some alpha. Okay, this is not 2, this is alpha. V1 into some scalar into V2. If this is true, then it is dependent. And we know that if it is not dependent, then independent. Okay, and what about these two vectors? Is it a multiple of other? One of them is multiple of other? No, answer is no. One of them is not a scalar multiple of other. If you take some 3 into 1, 1, that is give only 3, 3. If you take minus 1 into 1, 1, that is give minus 1, minus 1, not minus 1, 1. Okay, and conversely. So this is not a scalar multiple of other. So it is guaranteed that this set is linearly independent. So we verify the first one. So this is linearly independent. Next you have to check whether, or you can use our original method. Original method means C1 V1 plus C2 V2 equal to 0 and check whether all CIs are 0. If all CIs are 0, then it's linearly independent. But for in the case of two vectors, this is easy. You simply check whether they are multiple or not. If it is multiple, dependent, otherwise independent. Okay. Next you have to check whether, what about the span? If we have to check whether span of this V1 V2 equal to R square or not. If it is R square, then okay, it satisfies two conditions, then you can say that this is a basis. Okay, then how to verify span of V1 V2 equal to R square or not? Okay, anyway, it is clear that our vectors V1 and V2 belongs to R2, right? They are two tuples, they belongs to R2. Then we know that we have a result. Result is like this. If B is a subset of vector space V, then what about the span? This is nothing, this is span of B. Span of B is always subspace of the vector space V. You got it? Suppose B is a subset of V and V is a vector space, then you think about the span of B. Span of B means set of all linear combination of elements from B. Right? And we know that the span of B is also a subspace of V. Subspace means it is at least a subset, right? So one side is very clear. Span of B is subset of R2. That is from our property of spanning set. Okay. Then we have to check whether they are equal or not. That is our common technique. What is our common technique for proving two sets are same? For example, we consider a set A and B. We have to show that these two sets are same. The common practice is, first of all, we have to show that A is subset of B and we have to show that B is subset of A. If A and B satisfies these two conditions, then automatically they are same. A is subset of B and B is subset of A. This implies what? This implies A equal to B. Okay. So here one side is already trivial. Span of B subset of R square. So next we have to check whether the reverse part. So we have to check which condition. R square is a subset of span of B, right? R square is a subset of span of B. And how to check a how to check B is a subset of A. For that, we consider an arbitrary element. First of all, we consider the arbitrary element from arbitrary element from B. Then check whether is it belongs to A. This is true for all the elements in B. Then it is clear that B is a subset of A. Right? You choose an arbitrary element from B and check whether it is belongs to A or not. If it is belongs to A, then the conclusion B is subset of A. So similar technique is applied for this condition. Our aim is to check R square is a subset of span of B or not. Okay, so that we consider an arbitrary element from R square. What is the arbitrary element of R square? So you can treat an arbitrary element like this, AB. So AB is an arbitrary element from R square. Next we have to check whether this element belongs to span B or not. If this belongs to span B, that means all the elements of R square belongs to span B. That means R square is a subset, right? So how to verify this belongs to span B? If this is belongs to span B, then we can write this AB as linear combination of these two vectors. That means if it is possible, then you can write AB as some C1 into 1 1 plus C2 into minus 1 1, right? Suppose there exists such scalars, then you can say that AB belongs to span of B. Then how to check does there exist such scalars? Okay, that is easy. Now we have a system of equation containing two equations. If the system of equations is consistent or solvable, that means there exists C1 and C2. That means it is possible. Okay, so what is the system? Okay, this is our system of equation. A equal to C1 minus C2 and B equal to C1 plus C2. You can easily solve for these two. That gives C1 and C2. What is this? So C1 is A plus B by 2 and C2 equal to B minus A by 2. That means what? This system is consistent. That means this AB is arbitrary from R square. So every vector in R2 can be written as linear combination of these two vectors. That means every vector in R2 belongs to span of B. So as a conclusion, R2 is a subset of span of B. Right? So already we have this one, span of B is subset of R square. Now we have R square is a subset of span B. Combining these two, this implies span of B equal to R2, right? So we have now we verified two conditions. Linearly, this collection is linearly independent and span of this is equal to R2. So it is clear that this is a basis. Okay. Okay, this is a useful result. If V is a n-dimensional vector space, then any set containing more than n vectors is linearly dependent. Okay, if you know the dimension of the vector space, then if the collection contains more than the dimension, then it is always dependent. For example, you consider this example. Okay, it is clear that these vectors are belongs to R2, right? These vectors are belongs to R2. Then, so what is the dimension? Dimension equal to 2. And this collection contains 3 elements. More than n vectors, more than 2 vectors. So what is the conclusion? The conclusion is this is always dependent. Correct. So you can verify this is dependency using your original condition. That means you can find C1, C2, C3 such that not all of them 0 and their linear combination equal to 0. It is possible. Okay. Anyway, this is very easy condition. But this is possible only when dimension of V is not. Okay. This is another useful result. If V is a n-dimensional vector space, then any subset containing n linearly independent vectors spans V. So it is a basis. Okay, because already we know that dimension of V. We assume that dimension of V is not, that is n. Okay, then what about a basis? What about a basis? Since the dimension is n, we know that basis should contains n vectors, right? This result says that if any collection of n vectors is linearly independent, then automatically it spans. So no need to check span of this collection is equal to V or not. It's automatically spans. So this n linearly independent vector satisfies two conditions. It is already independent and spans, so it is a basis. Clear? So this result is also applicable only when the dimension of V is not. Okay. This result is also very useful for finding some new bases for a vector space if the dimension is not. Okay, so this is very useful. Okay, another result. If V equal to V1, V2, etc. Vn is a basis for a vector space V and V element of V, then the representation of V in terms of B is unique. Okay. This is a very important problem. So first we assume, okay, we have to show that for every vector has only one representation like this. Okay, it is possible because B is a unique. So we know that every vector can span elements from B. Okay, and this result says that that representation is unique. So first we assume that this V has two representation, and then we have to verify they are same or not. Okay, so we assume that this is for one representation. We assume that it has one more representation like this: d1 v1 plus d2 v2 plus etc. dn bn. Okay, anyway, its left hand sides are same, both are V. So you can equate the right hand side. So this becomes d1 v1 etc. plus cn vn equal to d1 v1 plus etc. dn bn. Okay, you can take this part to left side. So, and you can compare the similar vectors using our distributive property. So this becomes c1 minus d1 of v1 plus, so c1 minus d1 of v1 plus etc. plus cn minus dn of vn equal to 0. Yes, now we know this is a basis. We know that this collection is a basis. That means it is linearly independent, right? So v1, v2, etc. vn is a linearly independent, and you can think there are some scalars, some alpha 1, alpha 2, etc. alpha 1. They are like some scalars because c1 minus d1 is a scalar, c2 minus d2 is also a scalar. So a linear combination equal to 0, and they are independent. So what happened? So this implies c1 minus d1 equal to 0 and c2 minus d2 equal to 0, etc. cn minus dn equal to 0. This implies what? All Cis are equal to corresponding Dis. c1 equal to d1, etc. cn equal to dn. So what is our conclusion? There is only one representation. If you assume another representation like this, but now we have this scalars are same. That means every V has only one representation with respect to a basis B. If basis is different, yes, of course, automatically the representation is different. Okay, this result says that corresponding to a basis, it has only one representation. Okay, what is the advantage of this problem? You can convert every vector in terms of like this. That means corresponding to every vector, you can find a set of numbers. You got it? That means whatever be the vector space may be set of all signals or sound signals or some whatever be some higher dimension or matrices, whatever be, always we can represent every vector in terms of matrices, in terms of numbers. That is a main advantage. Okay, so that set of numbers is called the coordinate of this vector. So corresponding to every vector, there exists a unique set of numbers with respect to a basis, and that set of numbers are called coordinate of the vector, and this is the formal definition of the coordinate. If v equal to v1, v2, vn is a basis for a vector space V, and v equal to v belongs to V, then we know every V has a unique representation like this. Then you just pick that scalars c1, c2, etc. cn. These scalars are called coordinate of V with respect to B, and normally we denote this coordinate by a column matrix like that c1, c2, etc. cn. So whatever the vector space, every vector can be converted to like this in terms of numbers, and its converse is also true. Suppose you have a set of numbers, then you can recreate or you can regenerate the vector by taking the linear combination. If you know the coordinate is 1, 2, and also you know the basis, yes, you simply take 1 into that plus 2 into the second basis element, that gives the original vector. Okay, so you can convert everything, every vector in terms of numbers, and if you know the coordinate, then you can find the vector. Okay, so this is the main advantage of coordinate. Answer this problem. Find the coordinate of the vector b is equal to 3, 2 with respect to the basis b1 equal to this one and b2 equal to this one. Okay, anyway, it is clear that both are bases because we know they are belongs to R2 and its dimension is 2, and there are two linearly independent vectors. This is a set of two independent set. This also set of two independent set. So it is always spans. So they are bases. Okay. Why it is linearly independent? One of them is not a multiple of other. That's enough. Then how to find the coordinate of this v with respect to b1? So we have to find coordinate of v with respect to b1. So to find this coordinate, we have to write v is equal to some c1 into 1 0 plus some c2 into 0 1. And what is our v? V is 3 2. So 3 2 equal to c1 into 1 0 plus c2 into 0 1. Then what about c1 and c2? Yes, it's a very simple equation. This expression directly gives c1 equal to 3 and c2 equal to 2. Right. So what is this coordinate? We always represents coordinate like a column vector. So coordinate is 3 2 with respect to the basis b1. Right. So this is the idea. So next one, we have to find the coordinate of same 3 2 with respect to next basis. That means c1 into 1 1 plus c2 into minus 1 1. Then how to solve this c1 and c2? Okay, we have seen that we can write c1 as a plus b by 2. If it is ab, then this is a plus b by 2. And what is c2? B minus a by 2. So what about c1? Yes, c1 is 5 by 2 and c2 is equal to minus 1 by 2. Right? Because a plus b, 3 plus 5 by 2, and this is 2 minus 3 minus 1 by 2. So this is the coordinate of v with respect to b2 equal to 5 by 2 minus. Okay, so with respect to a basis, this coordinate is unique, and coordinate is differ with respect to the basis. If you change the basis, automatically coordinate is also different. Okay. But in later sessions, we will see there is a strong relation between these two matrices. Suppose we have different matrices with respect to different bases for a particular vector, then there is a strong relation between them. We will see in later sessions. Okay. Next problem, find the coordinate of the vector v is equal to 4, 3, 6, 2 with respect to this basis. Okay, anyway, it is given that this is a basis. Clear? It's a 4 element set, and we know the dimension of this space. This is belongs to which space? M2 by 2. Its dimension is 4. Okay, its dimension is 4. So to check whether it's a basis, you have to check only if they are linearly independent or not, because it contains only 4 elements. Okay. Anyway, in this problem, it is given it's a basis, no problem. So our aim is to find the coordinate. How to find the coordinate? First, you have to write this vector in terms of these vectors and find the scalars. Yes, this is our expression. This is equal to linear combination of these 4 vectors. Then this gives a system of linear equation, a system containing 4 equations. They are okay. By solving this system of a linear equation, you can find a unique set of C1, C2, C3, C4. Okay, that is possible because this is a basis. So you can find a unique set of C1, C2, C3, C4. Okay, you can solve either in normal method by eliminating this arbitrary constant or eliminating these unknowns, or you can use Gauss elimination method. Okay, so you can solve the system using Gauss elimination method. Okay, anyway, its solution is C1 equal to 1, C2 equal to 2, C3 equal to minus 1, and C4 equal to 4. So what is the coordinate? So the coordinate of V with respect to this basis B is a column matrix. The coordinate is always a column matrix. 1, 2, minus 1, sorry, 3. Right? Yes, V with respect to B is nothing. This column. Okay, so you already see that if you know the coordinate, then you can construct this vector, right? How? You simply consider the linear combination. If you know the vector, if you know, suppose the coordinate of a another vector, some v1 is equal to something like uh, some u, something like 7, 4, 3, 2, then you can construct this u, right? If you know the if you know the coordinate of u with respect to b is non, this is a column matrix, then you can construct u. How? You simply consider 7 times this one plus 4 times this one plus 3 times this one plus 2 times this one. This gives the corresponding vector. Okay, so this is the another advantage of this coordinate. We can reconstruct the vectors. If the coordinate of a vector is non, then we can reconstruct the corresponding vector. Okay, this is your homework. Thank you.